Okay, so let's close out this brief introduction to carbon cycle with a couple of things we have already seen before. We saw this long time series of going back to about 800,000 years from the Vostok ice core in or Epica Dome from Antarctica, and we talked about the abrupt increases and slow decreases with a range of about 80 to 100 ppm, going into deglaciation and glaciation. We talked about why the melting phase is very rapid and the glacier buildup is much slower, and how we have gone beyond anything we have seen in the last several million years when it comes to atmospheric carbon dioxide concentration, right? We had gone between 200 and 280 ppm in this record, and now we are at 415 or so. So the consequences have to be understood, and we already looked at what some of them are. Zooming into the last millennia or so, we went from 280 ppm since, let's say, the beginning of the Common Era to the Industrial Revolution, and then we have been increasing super exponentially, again going from the steady-ish Holocene concentration of 280 ppm into the Anthropocene, zooming to 415 now and increasing every year. So we talked about various aspects of carbon cycle. We looked at AFC-CO2 fluxes, where in the ocean anthropogenic CO2 is going. But if you look at the whole picture, this is showing the balance of sources and sinks globally averaged, going from 1850 to 2018. 1850 shows up all the time. It's not necessarily the actual beginning of the Industrial Revolution. It's just that that's when we have a lot of data starting from. Okay, so here are the CO2s below the long-term average and above. Sorry, the sinks and the sources. So negative means CO2 is being taken down, and positive means CO2 is being emitted. Okay, so we are looking at sources largely being the fossil fuel burning, fossil carbon, and land use change. There are little things there like cement production, etc., energy production, and other things. Energy production can be related to fossil fuel burning, of course, if you have a coal power plant. But land use change is deforestation and urbanization and other things which essentially produce CO2 as well. Okay. We are now around 40 to 50 gigaton carbon per year. We have a very good handle on how much fossil fuel carbon we are emitting, because from the beginning with coal burning and then petroleum and natural gas and so on, it's a very valuable commercial product. So very detailed accounts are kept of how much was produced, how much was sold, how much was bought, how much was consumed, and so on. So this number is pretty solid. We know very well how much we are emitting. So the total sources, we are already close to 50 gigatons of CO2. There is a difference between doing carbon and carbon dioxide. There is a conversion of 3.7 or so. So you have to be careful with what is being talked about. Here it's CO2. Okay, I didn't mention that before, but I'm sure you are aware, or maybe you are aware. If you're not, you should be. Okay, what are the sinks? We said ocean takes up about a quarter of the total emissions, so we are around 8 to 10 gigaton CO2 per year. Land sink, which is includes basically forest take-up, vegetation growth, wetlands, and all kinds of other sinks of carbon dioxide on land, and the remaining obviously can be measured in the atmosphere. So atmosphere is accumulating something which is not the total, because ocean and land are still taking up CO2, and as the source has increased, their sink size has also increased, and there is some missing sink. Total estimated sinks, if you take the total here and these totals, that don't match. So to some extent we don't know where some of the carbon is going. We can measure the atmosphere easily, we can estimate the land, we can estimate the ocean, but these are estimates. Okay, so we have to be careful. Nonetheless, there are places in the historical period where the numbers don't match, and the numbers that remain, the residual that remains when you add up atmosphere, land, and ocean, is now smaller and smaller, because we have better data and we have better estimates of all the sinks. Okay, so this is how carbon is getting distributed. As we said, the big challenge is to figure out if the ocean as a sink is getting saturated. In addition to acidification, will its ability to continue to take up CO2 continue to increase with CO2 increase, or will it saturate? Because with warming, dissolution also goes down. If warming goes all the way to the bottom, storage capacity goes down, because pressure, temperature are critical for dissolution, right? So atmosphere, of course, continues to grow. We can keep on pumping more into the atmosphere. As we said, during the time of the dinosaurs, estimated CO2 concentrations in the atmosphere were of the order of 1,000 ppm, much higher than now, but we don't want to go there now. But if you remember our future scenarios, RCP 8.5 will get us there by 2100, unless we find ways to reduce our emissions and also draw down what is already emitted. So we will never go to net negative emissions, but what will happen is we will emit CO2, but somehow we have to figure out taking down more CO2 from the atmosphere than we are emitting. The technology is needed for that. The place to hide it is needed. Right now, CO2 is being used to pump out more oil, or there are efforts to liquefy it and put it in the deeper ocean, into salt mines here and there and there and there. But no scalable methodologies exist right now, unless we spend a lot of money to pump CO2 elsewhere and capture it from the atmosphere. So big problem on our hands. So renewable energy sources has to grow up. Our carbon intensive lifestyle has to go down. GDP growths have to become less energy intensive. Energy has to become less carbon intensive. That's the story of carbon cycle and our impact on the planet.